In the vacuum inside every atom of your body, a number is sitting where it should be impossible. The equations say the Higgs mass should explode to 1 trillion times its size. It sits still instead. CERN is hunting the particle that decides whether it stays there. Tonight, a quark that drags the vacuum down, a twin that refuses to appear, and a universe balanced on a knife edge. Like and subscribe if this grips you. Prepare yourselves. We begin. The line outside the auditorium started forming the night before. It was the summer of 2012 at CERN, on the border between France and Switzerland. Physicists brought sleeping bags and slept on the floor of a hallway. Some of them had spent 30 years of their lives waiting for this one morning. Inside, an 83-year-old man named Peter Higgs sat in the audience and waited to learn whether the idea he had published as a young lecturer, back when nobody cared, was true. It was. Two enormous detectors, buried 300 feet underground, had seen the same bump in the same place. The Higgs boson was real. The field that fills all of space was real. The room stood and cheered. Peter Higgs took off his glasses and wiped his eyes. Champagne appeared in a room full of engineers. The last empty box in the standard model got filled in, and the textbooks went to the printers. Then somebody read the number. The discovery came with a measurement attached. The Higgs boson has a mass, and that mass is about 125 billion electron volts. In plain terms, the Higgs weighs roughly as much as an entire atom of iodine, packed into something with no size at all. For most of the people in that room, the number was a triumph. For a small group of them, it was the beginning of the worst decade in modern physics. Here is what those people knew, and what the television cameras missed. Inside this theory, the Higgs mass behaves like a dial. Almost every other mass in the standard model is bolted down by rules, held in place by deep symmetries that forbid it from wandering. The Higgs mass floats free. The equations refuse to predict it. You have to go outside, build a machine the size of a city, measure the value, and hand the answer back to the math. So that is what they did. And when the theorist took that measured number and asked one simple question, the answer came back insane. The question was this: if you calculate the Higgs mass honestly, including everything the universe does to it along the way, what should the number be? The answer was a value so enormous that our measurement looks like a typo. The math wants a mass around 100 million billion times larger than what the detectors found. Line the two numbers up, and they differ by roughly 16 zeros. Picture measuring the width of a single atom and getting an answer the size of the solar system. Something is holding the Higgs mass down. Something is standing between a value that should be astronomically huge and the small, quiet number we actually live with. Physicists have a name for this. They call it the hierarchy problem. By a wide margin, it is the ugliest crack in the most successful theory human beings have ever written. And the strangest part is the identity of the culprit. The thing shoving the Higgs mass upward is already sitting in our textbooks. We discovered it in 1995. We produce millions of them at CERN every year, and we celebrate each one. That morning in 2012 closed one search and opened a far more uncomfortable one. Because before you can understand how a mass becomes unstable, you have to understand what mass even means for a thing with no parts, no surface, and no size. The Higgs has a mass. Nobody has ever explained where it comes from. Pluck a guitar string and it gives you one note, every time. Tighten it and the note climbs. Loosen it and the note drops. The string decides its own pitch, and the thing doing the deciding is tension. How hard the string fights back when you pull it out of place. Fields work the same way, and this single idea is the doorway to everything that follows. A field is a quantity that exists at every point in space. All of it, everywhere, at once. The room around you, the vacuum between planets, the inside of a neutron star. Each point carries a value. Most of the time those values sit still and you would never know anything was there. Hit a field hard enough and it ripples. That ripple is what we call a particle. An electron is a ripple in the electron field. Light is a ripple in the electromagnetic field. The Higgs boson is a ripple in the Higgs field. Every particle you have ever heard of is a disturbance in something that fills the universe. Now for the part that changes how you see mass forever. The mass of a particle is the stiffness of its field. That is the whole story. A field that fights back hard when you disturb it produces heavy, sluggish ripples. A field that barely resists produces ripples that fly at the speed of light and weigh nothing at all. Photons weigh nothing because the electromagnetic field has no stiffness whatsoever. The top quark is the heaviest thing we know because its field is rigid, tense, brutally hard to bend. So when we say the Higgs boson has a mass, we are saying something specific. We are saying the Higgs field has a certain tension built into it. Physicists draw this tension as a shape. Picture a bowl. The Higgs field sits at the bottom of it, at rest, and the steepness of the bowl's walls tells you how violently the field snaps back when you push it. A narrow, steep bowl gives you a heavy particle. A wide, shallow bowl gives you a light one. Roll a marble in a soup bowl and it wobbles slowly. Roll it in a shot glass and it rattles fast. Same marble, different walls. The Higgs mass is a statement about the curve of those walls, and here is where the trouble starts. Quietly, with no drama at all. The standard model can tell you the shape of that bowl for the electron, can tell you the shape for the photon. Symmetries lock those shapes in place and forbid them from changing. Try to move them, and the math screams. Ask the same question about the Higgs field and the math shrugs. The theory allows any curve, any stiffness, any mass at all, from a whisper to a value near the birth energy of the universe. There is no rule inside the equations that says which one nature chose. Physicists put the number in by hand. They measure the Higgs, they get 125, and they write it into the theory like a homework answer copied from the back of the book. For a while, that felt acceptable. Plenty of numbers get measured rather than derived. Then someone asked what the vacuum does to that bowl, because the bowl does not sit in an empty room. It sits inside space itself, and space, as it turns out, is the least empty thing in existence. In 1948, a Dutch physicist did a calculation that should have been a joke. Hendrik Casimir asked what would happen if you took two flat metal plates, polished them smooth, and held them a hair's width apart in a perfect vacuum. No air, no light, no particles, nothing between them at all. His answer was that the plates would push together. Nothing would shove them. That prediction sat on paper for 50 years, until laboratories got precise enough to try it. The plates move, the force is real. It has been measured over and over to high accuracy. Two objects surrounded by absolutely nothing are pressed together by the nothing itself. Here is why. Empty space is a boil. Quantum mechanics allows the universe to borrow energy, provided it pays the loan back fast. The bigger the loan, the faster it must vanish. So at every point in the vacuum, pairs of particles blink into existence, live for a span too short to imagine, and cancel each other out before the universe notices the debt. An electron and its opposite. A quark and its opposite. Every kind of particle that can exist, existing briefly, everywhere, always. These are called virtual particles. The name is a poor one because their effects are as solid as concrete. Take the hydrogen atom. Its electron sits at a certain energy, and the older equations predicted that energy beautifully. Their measurements showed the level sitting a tiny distance off. The gap comes from the electron being constantly jostled by the seething vacuum around it. That shift is now measured to more decimal places than almost anything in science. Or take the electron's magnetism. The simple theory gives one answer. Reality gives a slightly different one, and the difference comes entirely from the storm of virtual particles the electron drags around with it like a coat. That calculation matches experiment to about 12 digits. It is the most precisely confirmed prediction human beings have ever made, and every digit of it depends on empty space being full. So the vacuum is a machine. It runs constantly, at every point in every cubic inch of the universe, and it has been running since the beginning. Now put a field into that machine. Every field feels the boil. Every particle carries a cloud of virtual company, and that cloud has energy. And energy weighs something, so the mass you measure in a laboratory is never the raw mass of the thing itself. It is the raw mass plus everything the vacuum has piled on top. For the electron, the pile is small, manageable, a polite correction. For the Higgs, the pile is a catastrophe, because the Higgs field is the one thing in nature that every massive particle touches. That is its entire job. Every virtual quark, every virtual boson, every fleeting pair that flickers in and out of the vacuum reaches out and tugs on the Higgs field as it goes. Billions of loans, billions of tiny shoves, all of them landing on the walls of that bowl, and the shoves do not cancel, they add. The stiffness of the Higgs field, the number we measured to such celebration in 2012, is the sum of its own raw value plus every whisper the vacuum has ever contributed, which raises a question nobody in that auditorium wanted to say out loud. If the vacuum has been screaming at the Higgs field since the first instant of time, why is the field still so quiet? The answer starts with one particle, the heaviest one we have ever found. Try to measure an electron and you will never touch the electron. You touch what it is wearing. Every charged particle in the universe walks around inside a haze of borrowed matter. Virtual pairs flicker up around it, feel its charge, twist slightly, and vanish. New ones appear before the old ones finish dying. The haze never clears. It travels with the particle like a coat that cannot be removed, and it has been there since the particle came into being. That coat has energy. Energy has weight. So the electron you weigh in a laboratory is the electron plus the coat, forever bundled together, with no seam between them. Physicists gave the two pieces names. The raw particle underneath is the bare mass. The thing you actually measure is the dressed mass, and in the 1940s this simple picture nearly destroyed the whole field, because when the first generation of theorists sat down and calculated the weight of the coat, they got infinity, not large number. Infinity, arriving from the fact that the haze goes all the way down. Smaller and smaller virtual pairs, closer and closer to the electron, contributing more and more energy forever. Paul Dirac, who built the equation the whole mess came from, called the results ugly and refused to make peace with them for the rest of his life. The way out was found by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, working separately and arriving at the same trick. It goes like this. You never see the bare electron. You cannot. It has never existed on its own anywhere in the history of the universe. So stop trying to calculate it. Instead, take the measured mass from experiment, feed it back into the equations, let the infinite coat and the infinite bare mass swallow each other, and what survives is the difference, which is finite and which predicts the next experiment. This trick is called renormalization, and it works to an accuracy that borders on the absurd. 12 matching digits between chalkboard and detector. Something about it still bothers people. Feynman himself called it a shell game. Look closely at the shell game and you will notice something crucial. Two enormous numbers cancel almost completely, and the small leftover is the world we live in. Physicists made their peace with that arrangement for one reason, and one reason only. For the electron, the coat is thin. Run the calculation properly, including everything quantum mechanics allows, and the electron's correction grows with painful slowness. Push the theory up to energies 1 trillion times beyond anything we can reach, and the correction to the electron's mass climbs by a few percent. That is all. The bare electron and the dressed electron are close cousins. The coat weighs almost nothing, so the shell game never involved sleight of hand. The two numbers being cancelled were always modest, and the answer was never in danger. The Higgs plays a different game entirely. When you weigh the Higgs field's coat, the number does not creep upward. It rockets. The correction grows with the square of every energy scale you allow into the calculation, and there is no gentle logarithm to slow it down. Reach higher and the coat gets heavier fast, then faster, then absurdly fast. Same vacuum, same virtual particles, same math. One particle barely notices, the other gets buried. The difference between them is not luck. There is a rule protecting the electron written into the structure of reality, and the Higgs sits outside its shelter. Hold your right hand up to a mirror and watch a left hand wave back. Your hands cannot be laid on top of each other. Same fingers, same joints, same everything, and no rotation in the world will make one match the other. They are mirror twins, permanently distinct. Electrons come in two kinds, sorted exactly this way. Physicists call the property chirality, which is a fancy word for handedness. Every electron in existence is a blend of a left-handed piece and a right-handed piece. They are separate objects with separate rules. The weak force, the one that runs radioactive decay, only ever speaks to the left-handed piece. It ignores the right-handed piece completely, as though it were furniture. Here is where the armour comes from. An electron's mass is a bridge between those two halves. Mass is the thing that lets a left-handed electron turn into a right-handed electron and back again, over and over, trillions of times as it moves. A massless particle stays one-handedness forever because it travels at light speed and nothing can ever catch it to flip it around. Mass is the flipping. That is what mass physically is for a particle like the electron. Now imagine the electron's mass was zero. Something beautiful happens to the equations. The left half and the right half become entirely independent, two separate species with no bridge between them. You could rotate one and leave the other untouched, and the math would not blink. A new symmetry appears out of nowhere. Symmetries are the strictest laws in physics. When the equations have a symmetry, they will fight to keep it. So picture the vacuum trying to pile mass onto a massless electron. To do it, the vacuum must build a bridge between the two halves. Building that bridge breaks the symmetry, and the equations refuse, because a symmetry that exists at one energy exists at all of them. Give the electron a small mass, and the symmetry becomes slightly broken, though the protection survives. Every correction the vacuum tries to add has to be proportional to the mass that is already there. Small mass, small correction. The electron's own lightness is what keeps it light. Physicists call this a technically natural quantity, an idea sharpened by the Dutch theorist Gerard de Hooft. A number is safe if switching it off would hand the universe a new symmetry. The electron is safe. The quarks are safe. The photon has no mass at all, protected by a symmetry so rigid that a single photon mass term would collapse the entire theory of light. The universe protects almost everything. Then there is the Higgs. The Higgs boson has no handedness. It has no spin at all. It carries no direction, no left, no right, no orientation of any kind. Physicists call it a scalar, and it is the only fundamental scalar we have ever found. Set its mass to zero and watch what appears. Nothing appears. No new symmetry, no fresh rule, no structural change to the equations whatsoever. The Higgs at zero mass looks exactly as arbitrary as the Higgs at any other mass, which means nothing anywhere in the theory has a reason to care what its value is. The vacuum can pile on whatever it likes, and no law stands in the way. Every particle in nature wears armour. The Higgs walks out into the storm bare, and the biggest particle we know of is waiting for it. In March of 1995, two teams in Illinois announced they had found a quark that weighed as much as an atom of tungsten. The room went quiet rather than loud. The top quark had been hunted for 20 years. Every prediction said it would be heavy, and every prediction came in too low. Physicists searched, missed, raised their estimates, searched again, missed again. The particle kept retreating into the dark. When Fermilab finally cornered it, the number came back at roughly 173 billion electron volts. Sit with what that means. A single quark, one of the smallest things that exists with no measurable size at all, weighs about as much as an entire atom of tungsten. 74 protons, 109 neutrons, 74 electrons, all of that architecture matched by one indivisible point. It is 35,000 times heavier than the up quark sitting inside your fingertips. The gap between the lightest quark and the heaviest one is wider than the gap between a housefly and a blue whale. Nobody knows why. The top quark also dies faster than anything else in the universe. Every other quark, when created, immediately grabs partners and forms a proton, a pleon, something. The strong force is quick that way. The top quark is quicker. It decays before the strong force can reach it, in a span so short that light travels less than the width of a proton before the particle is gone. It is the only quark that lives and dies alone, naked, never bound to anything. Now connect it to the Higgs. A particle's mass comes from how tightly it grips the Higgs field. Weak grip, light particle. The electron barely brushes the field as it passes, which is why it weighs almost nothing. Every quark and every lepton in nature holds the Higgs field with a delicate apologetic touch. The top quark holds on with everything it has. When physicists measure the strength of that grip, they get a number close to 1. Perfectly, suspiciously close to 1, on a scale where every other particle scores a tiny fraction. The electron's grip is roughly 3 millionths. The top quark's grip is unity, the maximum the theory naturally allows, as though the top quark were made of the Higgs field. That grip works in both directions. The Higgs field gives the top quark its enormous mass, and the top quark in return reaches back and shoves the Higgs field harder than anything else in existence. Remember the boiling vacuum. Virtual top quarks appear and vanish everywhere, constantly, including inside the empty space that defines the Higgs field's own stiffness. Each pair grabs the Higgs with that maximum grip, tugs, and disappears. Every other particle contributes a whisper. The top quark contributes a hammer blow. Run the numbers and the top quark's contribution to the Higgs mass swamps everything else combined. Every other correction is a rounding error next to it. So the particle that makes mass unstable is already in our hands. We built a machine to find it, we celebrated when we did, and we manufacture tens of millions of them at CERN every single year. The top quark is pushing the Higgs mass upward right now, in the room you're standing in. The question is, how far up? Every calculation in physics needs a ceiling. You cannot add up the effects of virtual particles forever, so you draw a line and say, above this energy, my theory stops describing reality, and something else takes over. Then you calculate up to the line and stop. The question is where to put the line. For most of physics, the answer is easy, because the line moves and nobody cares. The correction creeps along so slowly that shifting the ceiling by a factor of 1,000 barely changes the answer. The electron shrugs. The Higgs mass grows with the square of that ceiling. Double the line, quadruple the correction, raise it by a factor of 10, and the correction jumps 100-fold. The ceiling's position stops being a bookkeeping choice. It becomes the whole answer. So where does the standard model actually break? There is one energy in nature that everybody agrees is a genuine wall. It is the point where gravity stops being negligible and becomes as strong as every other force. Squeeze enough energy into a small enough space and you make a black hole, and the equations of particle physics dissolve into gibberish. That threshold is called the Planck scale, named for Max Planck, who stumbled on it in 1899 while playing with the fundamental constants. The Planck energy sits at roughly 10 billion times the mass of a proton. Compare it to the Higgs. The Higgs boson weighs 125 units on the physicist's scale. The Planck energy weighs about 10,000 million billion of them. The gap is a factor of 100 million billion. Numbers that size stop meaning anything, so build a picture instead. Say the Higgs mass is the thickness of a single sheet of paper. On that scale, the Planck energy would be a stack reaching from your desk to the star Betelgeuse, 600 light-years away, and back again several times over. Now feed that ceiling into the calculation. The virtual top quarks do not stop at some polite energy. Quantum mechanics allows them to borrow any amount of energy at all so long as they return it quickly enough. So they borrow all of it, right up to the wall. Every top quark pair that flickers into existence, anywhere between here and the Planck scale, reaches out, grabs the Higgs field with that maximum grip, and shoves. Add up the shoves and the Higgs mass should land near the Planck scale itself. It should be 100 million billion times heavier than it is. Understand what that world would look like. A Higgs that heavy would give every particle a Planck-sized mass. Electrons would be microscopic black holes. Atoms could never form. Chemistry would never happen. The universe would be a thin fog of gravitational wreckage, dark and sterile for eternity. Instead, the Higgs weighs 125. We have stars, and you are made of carbon. Physicists have run this calculation 10,000 different ways since the 1970s. They have tried every reasonable ceiling. They have used every trick in the mathematical arsenal. The answer keeps coming back the same, and it keeps being wrong by the largest margin in the history of physics. There is a way to fix it. It takes one line of arithmetic, and any high school student could write it down. The fix is so grotesque that it has kept people awake for 50 years. Here is the escape route, and it is embarrassingly simple. Remember the two pieces. There is the bare Higgs mass, the raw value written into the equations before the vacuum touches it. And there is the correction, the mountain of virtual top quarks piling on top. What we measure is the sum. The correction is astronomically large and negative, so make the bare mass astronomically large and positive. Line them up. Let them cancel. Whatever survives is the Higgs we live with. That is legal. Nothing in the mathematics forbids it. The bare mass is a free parameter, which means nature is allowed to choose any value it likes, and we are allowed to write down the value that works. Now look at what the cancellation requires. The correction lands somewhere near the Planck scale, squared. The measured Higgs mass squared is a comparatively tiny number. For the sum to come out right, the bare mass and the correction must agree with each other to roughly 34 decimal places, and then differ by a hair at the 35th. Write it out as a picture. Imagine two numbers, each one 35 digits long. Every digit of the first matches every digit of the second, all the way down, position by position, until the very last one. There they differ, and that final difference is our universe. Stars, planets, chemistry, you, everything, living in the 35th digit of a coincidence. Change one digit anywhere higher in the sequence and the world ceases to exist. There is a classic way to feel this. Picture two mountains, each one exactly as tall as the distance from here to the sun, standing side by side. Measure their heights, subtract one from the other, and get a difference of 1 millimeter. The width of a grain of sand. That is the arithmetic the Higgs mass demands, and nothing in the theory tells the mountains to be that closely matched. The word physicists use is fine-tuning, and it carries real contempt. Because the two numbers have nothing to do with each other. The bare mass comes from whatever wrote the laws at the beginning of time. The correction comes from the top quark, discovered 14 billion years later by primates in Illinois. These are separate facts about the universe, arriving from entirely different directions, and they agree to 34 decimal places. That is the shape of the hierarchy problem. It has been stated in its modern form since the late 1970s by Kenneth Wilson, by Leonard Susskind, by Gerard de Hooft, and it has never moved an inch since. The standard model works. That is the maddening part. It survives every test we throw at it, predicts every measurement, matches every detector. It is simply balanced on a knife edge so absurdly thin that most physicists refuse to believe the balance is an accident. So they went looking for the mechanism, something that reaches into the calculation and cancels the top quark's shove automatically, without anyone hand-tuning digits. Some new particle, some new symmetry, some hidden piece of machinery holding the Higgs mass down. 50 years of theory came out of that search. Careers were built and spent on it. The Large Hadron Collider itself was designed in large part to find whatever was doing the holding, and a growing number of physicists now suspect the entire argument may be a mirage, that nature owes us no explanation whatsoever, that 34 digits of luck is simply how it is. That fight has become the most bitter disagreement in modern physics. A young physicist at CERN once described the situation as a religious war conducted with equations. He was joking. Slightly. The argument runs like this. One camp says the fine-tuning is a scandal, a flashing red light, proof that something is missing from our picture. The other camp says the whole complaint is a matter of taste dressed up as science. Take the second position seriously, because it is stronger than it looks. What law of physics says numbers must be reasonable? Where in the equations is it written that parameters have to look tidy to a human being? The universe is under no obligation to be comfortable. Perhaps the bare Higgs mass simply is what it is, set once at the beginning, and our discomfort is a fact about primate psychology rather than a fact about nature. There is also a sharper objection. Sharper. The whole calculation depends on the bare mass being a real thing, a physical quantity that exists somewhere. Nobody has ever measured it. Nobody ever will. It is a bookkeeping entry in a theory we already know is incomplete. Getting alarmed about the size of an unmeasurable number may be a category error, and the fine-tuning depends on where you put the ceiling. Move the wall down and the crisis shrinks. Nobody has proven the Planck scale belongs in that calculation at all. Now hear the first camp, because they have history on their side. Their claim is that fine-tuning has been a reliable alarm bell for 100 years. Every previous time physics found two enormous numbers cancelling for no reason, the cancellation turned out to have a cause, a hidden particle, a hidden symmetry, something real, waiting to be found. The tuning was never a coincidence. It was a clue, and following the clue produced some of the greatest predictions ever made. The argument has a name, and it comes from a single sentence Hooft wrote in 1979. A small number is allowed to be small if setting it to 0 makes the theory more symmetric. Otherwise, the smallness demands an explanation. By that standard, the Higgs mass is the most unnatural number in science. Both camps are staffed by brilliant people. Both have watched the argument grow personal because there is money involved, and time, and lives. The Large Hadron Collider cost billions and consumed the working careers of a generation. It was built on the promise that something would appear alongside the Higgs to explain the tuning. Whole theoretical industries grew around that promise. Textbooks were written. Graduate students were trained in the mathematics of a particle nobody had seen. If the tuning has no explanation, all of it was chasing a ghost. If the tuning does have an explanation, the machinery is out there, and we have been searching in the wrong place. The stakes are the direction of physics for the next 50 years, and possibly the last enormous machine our species will ever build. Before choosing sides, one thing deserves a fair hearing. The people who trust the alarm bell are trusting it because it has rung before. Twice, in the last 100 years, physicists heard a number that made no sense, refused to accept it, and predicted a particle out of pure discomfort. Both times, the particle was there. Both times, it changed everything. In 1930, the electron was on the verge of destroying physics. The problem was its own electric field. An electron carries charge, that charge creates a field, and the field carries energy. Squeeze the electron smaller and the field's energy climbs. Treat the electron as a true point with no size, which is what every experiment insisted, and the energy runs to infinity. So the electron should have weighed infinity. It weighs almost nothing. To make the arithmetic work, physicists had to cancel an infinite field energy against an infinite bare mass, and pray the leftover came out right. They hated it. Wolfgang Pauli called the whole business a scandal. Then Carl Anderson took a photograph. In 1932, in a cloud chamber on a mountain in California, a track curved the wrong way. Same mass as an electron, opposite charge. Anderson had photographed the positron, the electron's mirror twin, which Paul Dirac had predicted on paper from nothing but the demand that his equation make sense. 2 years later, Victor Weisskopf redid the electron self-energy calculation, with the positron included. The infinity collapsed. Virtual positrons appear around the electron and screen it. They push where the electron pulls. The two effects nearly cancel, and what had been a runaway disaster became a gentle, slow correction. The electron's mass was safe. The scandal evaporated, and the fix arrived in the shape of a particle nobody had known existed. The pattern repeated 40 years later, and this time the discomfort came first. In the 1960s, physicists studied a particle called the kaon. The theory of the day said kaons should sometimes decay into a pair of muons, and the calculation gave a rate that was easy to check. Experimentalists checked. The decay was there, roughly 1 billion times rarer than predicted. Every term in the calculation looked correct. The number was simply, brutally wrong. 3 theorists, Sheldon Glashow, John Iliopoulos, and Luciano Maiani, looked at the arithmetic in 1970 and noticed something. If a fourth quark existed, unknown, unseen, with the right properties, its contribution would arrive with the opposite sign and cancel the offending term almost exactly. The suppression would fall out automatically. They had no evidence. They had a number that made them uncomfortable, and a cancellation that was too neat to ignore. In November of 1974, 2 laboratories on opposite coasts of America found the charm quark within days of each other. Physicists still call that week the November Revolution. The theorists had been right, 4 years early, working from nothing but the refusal to accept a coincidence. That is the track record the naturalness camp keeps pointing at. Twice, an unexplained cancellation was the signature of a missing particle. Twice, the missing particle showed up with exactly the properties needed. In both cases, the new particle arrived as a partner, carrying the opposite sign, arranged so that the dangerous terms killed each other. Look at the Higgs problem with that history in mind, and the shape of the answer seems obvious. The top quark shoves the Higgs mass upward. Something must shove back. You need a partner for the top quark. Same grip on the Higgs, opposite sign. Then the cancellation happens automatically, forever, with no digits tuned by hand. In 1971, a Russian physicist wrote down a symmetry that would deliver exactly that. Not for one particle, for every particle in existence. Everything in the universe belongs to one of 2 families, and the families hate each other. The first family is the fermions, quarks, electrons, neutrinos. They are the stuff of matter, and their defining trait is stubbornness. No two identical fermions will occupy the same state. This refusal is why atoms have structure, why chemistry works, why you cannot push your hand through a table. Matter takes up space because fermions will not share. The second family is the bosons, photons, gluons, the Higgs. They are the carriers of force and they are gregarious. Pile as many into one state as you like. A laser beam is 1 trillion photons doing exactly that, marching in identical lockstep, stuff and force, loners and joiners. For most of the 20th century, they looked like two unrelated kingdoms with no bridge between them. In the early 1970s, a handful of theorists found the bridge, and it was gorgeous. The idea is called supersymmetry, and it says the two families are the same family seen from different angles. Every fermion has a boson twin. Every boson has a fermion twin. Rotate the universe in a direction that does not exist in ordinary space, a direction made of pure quantum bookkeeping, and matter turns into force and back again. If that symmetry is real, the particle list doubles. The electron gets a boson partner, the photon gets a fermion partner, every quark, every lepton, every force carrier acquires a shadow twin that has been hiding since the beginning of time. Physicists gave the twins goofy names: the selectron, the photino, the gluino, the squark. It sounds like a children's cartoon, which has done the theory no favours in the public imagination. Then comes the miracle, and it is the reason this idea took over theoretical physics for 30 years. Fermion loops and boson loops contribute to the Higgs mass with opposite signs. That's a hard mathematical fact, buried deep in the structure of quantum field theory, and it has been known since the field was young. When a fermion flickers through the vacuum and shoves the Higgs, it shoves one way. When a boson does the same, it shoves the other. Now give the top quark a boson twin with identical grip on the Higgs field. The top quark shoves the Higgs mass upward toward the Planck scale. Its twin shoves downward with the exact same strength. The two terms meet in the equation and annihilate each other, digit for digit, all the way down, automatically with nobody tuning anything. The mountain of virtual corrections vanishes. The Higgs mass sits wherever it likes, protected, stable, sensible. And the cancellation happens for every particle at once. Every fermion has a boson holding its hand. The entire storm cancels itself. Supersymmetry also does things nobody asked it to do, which is usually the mark of a good idea. It hands over a dark matter candidate for free in the form of the lightest twin, a stable particle that barely interacts with anything. It makes the three forces of the standard model converge to a single strength at high energy, which they refuse to do without it. It shows up naturally inside string theory. One idea. 4 separate problems solved. There was only one condition attached, and the entire theory lived or died on it. The twins had to be light enough for us to find. Supersymmetry comes with a fatal complication, and it was obvious from the first day. The selectron would weigh exactly what the electron weighs. The photino would be massless like the photon. Twins mean twins. Same mass, same charge, same everything except the family they belong to. A boson twin of the electron, weighing as much as an electron, would have been discovered in 1930. It would sit in every atom. It would be in your body right now, and chemistry would look nothing like it does. So the symmetry is broken. The twins exist, and something in the early universe made them heavy, which is why we have never seen one. The theory survives. Now the crucial question, and everything hinges on it. How heavy? Push the twins up to the Planck scale, and supersymmetry becomes useless. The cancellation only works when the two partners match. Separate them, and the cancellation degrades. The bigger the gap between a particle and its twin, the more of the original mountain leaks back into the Higgs mass. So the twins have to be heavy enough to hide from every experiment ever conducted, and light enough to keep the Higgs mass from exploding. That window is the whole game. Run the arithmetic and the window has a hard edge. To keep the Higgs mass in place without hand-tuned digits, the relevant twins must weigh somewhere below about 1,000 billion electron volts, roughly 8 times the Higgs. That number was the promise. It is written into the design documents of the Large Hadron Collider. It is why the machine's energy was chosen. Physicists were not guessing when they built a 27-kilometre ring under the Alps. They were aiming at a target the theory had painted for them, and one twin mattered more than all the others. Remember who is doing the shoving. The top quark dominates the correction so completely that every other particle is background noise. Cancel the top quark's contribution, and you have solved 90% of the problem, whatever the other twins are doing. So the top quark's partner became the most important undiscovered particle in physics. It has a name that sounds like a typo. The stop. The stop is a boson. It carries color charge, which means the Large Hadron Collider can manufacture it in bulk, because the machine smashes protons and protons are made of color-charged debris. It holds the Higgs field with the same maximum grip its partner does. It was, by every argument available, the single most predicted particle of the modern era. The other twins could hide. The squarks of the lighter quarks could be pushed to enormous masses without hurting anything, because those quarks barely touch the Higgs. The theory could shed almost all of its baggage and keep working. The stop could not hide. The whole logical structure rested on it being findable. Physicists went in with confidence, and they had reason to. Estimates published before the machine turned on suggested the discovery might come within the first year of running. The Large Hadron Collider fired its first beams in 2008. It found the Higgs in 2012. Then the searches began in earnest. Thousands of physicists across 2 detectors, hunting the particle that had been promised to them. What happened next has been called the most important negative result in the history of science. The stop leaves a beautiful signature, at least on paper. Make a pair of them in a collision. Each one decays into a top quark and a lightest twin particle, and the lightest twin is the dark matter candidate, meaning it slips through the detector without touching anything. So the event looks like 2 top quarks flying out in one direction, while a large chunk of momentum simply goes missing. Momentum is conserved. If the visible debris in a collision does not balance, something invisible left the building. That imbalance is the fingerprint, and it is exactly what Atlas and CMS were built to catch. The searches started in 2010. Every energy upgrade brought a new campaign. Every year of data brought new analyses, new machine learning techniques, new ways to slice the collisions. The results came back the same, over and over, in language that grew heavier each time. No excess observed. Consistent with standard model expectations. By the end of the first run, the exclusion had climbed past 700 billion electron volts. The natural window was still open, and people stayed calm. The machine went down for 2 years and came back at higher energy in 2015, which multiplied the production rate enormously. The window closed anyway. By the end of Run 2, stops lighter than roughly 1,300 billion electron volts were excluded in the simplest scenarios. Gluonos, the twins of the gluon, were pushed past 2,200. The squawks of the ordinary quarks were driven above 1,800. The natural window, the one the theory had promised, was gone. Here is what that means in practice. Supersymmetry survives. The theory has enough parameters to hide behind, and the twins can always be pushed higher. What died was the reason for believing it. Every billion electron volts of exclusion makes the cancellation worse. Separate the top quark from its stop by a factor of 8, and the 2 contributions stop matching. A remainder leaks through. To keep the Higgs at 125, someone has to tune the digits again by hand. Current limits put that tuning at roughly 1 part in 100, and worse in many models. Supersymmetry was invented to cure fine-tuning. It now requires fine-tuning to survive. The idea has eaten itself. There is a particular kind of grief in that outcome. An entire generation of theorists spent their careers on this. Some of them wrote hundreds of papers about a particle that never arrived. Nima Arkani Hamed, one of the sharpest theorists alive, has said publicly that the results forced him to reconsider everything he thought he understood about how nature works. Others simply left the field. The machine did its job perfectly. It looked exactly where the theory said to look, with more precision than anyone expected, and found empty space. That is science functioning correctly, and it feels terrible. Now comes the uncomfortable part, and it is the reason this story continues rather than ends. Every one of those exclusion limits carries a footnote. Each one assumes the particle decays a certain way, into certain products, leaving a certain trail. Change the assumption, and the limit evaporates. there is a region of the search where the stop becomes almost invisible, where it can sit at a perfectly natural mass, hiding in plain sight. It hides by pretending to be the very particle it was born to cancel. The Large Hadron Collider produces tens of millions of top quark pairs every year. They are the most ordinary interesting thing the machine makes. Two protons collide, a pair of top quarks appears, each one decays instantly, and the detector fills with jets of debris and a splash of missing momentum from the neutrinos that escape. The physicists log it and move on. It is background, wallpaper. Now suppose the stop weighs a little more than the top quark. Say the difference between the stop and the invisible twin it decays into is almost exactly the top quark's mass. Watch what happens. The stop decays into a top quark and an invisible particle. The invisible particle barely moves because there was almost no energy left over to give it a kick. So it drifts out of the collision carrying nearly nothing. All the detector sees is a top quark and a whisper. Two stops decaying this way produce two top quarks and two whispers, which is indistinguishable from two top quarks and two neutrinos. The signature the physicists spent decades designing has collapsed into the background it was supposed to stand out from. There is no missing momentum to speak of because the invisible particles were born too slow to steal any. The event lands in the pile with the millions of ordinary top pairs and disappears forever. Physicists call this a compressed spectrum, and the region where it bites is called the stealth stop window. It gets worse, and this part is genuinely strange. Quantum mechanics does not let you separate a stop event from a top event and count them individually. When two processes produce the same final state, the amplitudes add before anything gets squared. The stop signal and the top background interfere with each other, like two ripples on a pond meeting and partly cancelling, so a stop hiding in this window does not add a small bump to the top quark count. It subtly reshapes the entire distribution, shifting it by a percent here and a percent there, in ways that depend on how well you understand the ordinary process you are comparing against. The limiting factor stops being the detector. It becomes the theory calculation of the background itself. Physicists have attacked this window from every angle. They measure the top pair production rate to fractions of a percent and compare against ever more sophisticated predictions. They look at how often the tops come out spinning in correlated directions, because a stop, being a boson with no spin, would wash that correlation out. They hunt for tiny distortions in how the debris shares its energy. The measurements keep landing close to the standard model prediction, though the uncertainties in this precise region remain large enough that a stop of the right mass has never been fully ruled out. Sit with the possibility. The particle that saves the universe from a Planck-sized Higgs mass might have been produced millions of times inside CERN already. It might be sitting in the archived data from 2018, recorded, saved, backed up on tape, mixed into a haystack of events that look exactly like it. We would have made it. We would have caught it, and we would have filed it as background. Hiding by imitation is one trick. There is another trick, and it is worse, because it exploits something the detectors were designed to throw away on purpose. Atlas and CMS see about 40 million proton crossings per second. Storing that would fill every hard drive on Earth in under a day. So the detectors throw almost everything away, immediately using a system called the trigger. Custom electronics look at each event for a few millionths of a second and make a decision. Keep or delete. Roughly one event in 40,000 survives. The rest are gone before any human being knows they happened. The trigger has rules, and the rules were written by people who assumed something. They assume the interesting particles decay instantly, right at the collision point. Every heavy particle we know does. The top quark dies in less time than light takes to cross a proton. The Higgs dies faster. In all of particle physics, the pattern is nearly universal, so the electronics were tuned to look for tracks pointing straight back to the center of the machine. Anything that decays somewhere else looks like a glitch. Now consider what a broken symmetry can produce. In many versions of supersymmetry, and in a long list of other theories, the new particle has almost no way to decay. Perhaps the only channel available is heavily suppressed. Perhaps it must pass through a very heavy intermediate step. The particle then lives a long time by particle physics standards, which can mean a billionth of a second or a millionth. A billionth of a second is enough to travel a foot. So the particle is made at the center. sails outward through the tracking layers, leaving nothing behind, and then decays in the middle of the calorimeter, spraying debris that points nowhere. Or it exits the entire detector and dies in the rock outside, or it stops inside the metal, sits there, and decays hours later during a quiet period between beams. Every one of those signatures would have been discarded as noise. Physicists realized the gap and started plugging it. There are now searches for displaced vertices, where tracks appear from empty space with no parent. There are searches for tracks that vanish partway through the detector, because the particle decayed into something invisible and left a stub. There are searches for slow particles, arriving late, because anything heavy travels well below light speed and shows up in the timing. Then came the strangest proposals of all. If a particle can escape the detector entirely, build another detector outside. FACER sits in a service tunnel almost 2,000 feet down the beamline from the collision point, behind 100 meters of rock, waiting for anything weakly coupled enough to have flown through solid stone. It began taking data in 2022 and has already detected collider neutrinos, the first ever seen at an accelerator. Others have been proposed, enormous empty boxes on the surface above the collision hall or tucked into cavern corners whose entire purpose is to sit still and watch for something drifting out of the earth and decaying in midair. We are building instruments to catch the things our instruments were designed to miss. None of these has found the stop. The searches are young, the coverage is patchy, and the window stays open. Underneath all of it sits a possibility more radical than any hiding particle. It says the search has been wrong from the start. It says the Higgs was never fundamental. The pion should have the same disease as the Higgs. It is a boson. It has no spin. By every argument in this story, its mass should be dragged to the Planck scale by the boiling vacuum. Instead, the pion weighs about 1/7 of a proton, sitting quietly, protected, stable in exactly the way the Higgs should be and is not. The pion gets away with it for one reason. The pion has parts. Look inside and you find a quark and an antiquark, bound by the strong force. It is a composite object, roughly 1/millionth of a billionth of a meter across, with structure and size and internal machinery. Above a certain energy, the pion stops existing as a particle at all. Probe it hard enough, and you see the quarks instead. That size is a ceiling, and it is a real one. The runaway calculation needs an infinite tower of energies to do its damage. A composite particle cuts the tower off, because above its own binding scale the particle dissolves and the question stops making sense. The virtual corrections never get anywhere near the Planck scale. They stop at the pion's own doorstep and the mass stays where it is. So apply the same idea to the Higgs. Perhaps the Higgs boson is a bound state. Perhaps there is a new force, far stronger than any we know, and a new set of constituents we have never seen, and the Higgs is what they make when they stick together. The hierarchy problem would evaporate on contact, because the runaway would stop at the Higgs boson's own size. The idea is called compositeness, and it is old. It was born in the 1970s as Technicolor, a direct copy of the strong force pasted in at higher energy. That first version died. It predicted the Higgs would be heavy, hundreds of billions of electron volts, a broad and messy object. The Higgs we found is light, narrow, and behaves almost exactly like a fundamental particle should. The idea came back in a smarter form. In the modern version, the Higgs is a composite object with a special pedigree. It is the leftover of a broken symmetry, the same mathematical accident that makes the pion light. Particles born that way are naturally much lighter than the stuff they are made of. A Higgs of 125 could then sit comfortably below constituents 10 times heavier. Here is how you would catch it. A composite Higgs would grip other particles slightly differently than a fundamental one. Its couplings would drift, by a few percent in a specific pattern. So physicists have measured every Higgs coupling they can reach. How strongly it grabs the top quark, the bottom quark, the tau, the W and Z bosons, the suon. Every measurement so far agrees with a perfectly fundamental Higgs, within uncertainties of roughly 5 to 10%. That agreement pushes the constituents above about 1,000 billion electron volts, and every improvement pushes them higher. The composite Higgs is being squeezed the same way supersymmetry was, by silence rather than contradiction. Both escape routes assume the same thing, that whatever cancels the top quark must be something we can see. There is a version where the rescuer carries no charge we can grab, where it feels no strong force, no electricity, and passes through the largest machine ever built like a ghost through a wall. Before that, there is one more visible candidate, a quark that breaks the deepest pattern in the Standard Model. Every quark in the Standard Model gets its mass the same way, and that shared origin is the source of all the trouble. A quark comes in two-handed halves, and the halves behave differently. The left-handed half feels the weak force. The right-handed half ignores it. Because the two halves have different personalities, no law can simply hand the quark a mass, since mass requires bridging them. So the Higgs field does it. The Higgs steps in, connects the two mismatched halves, and mass appears. Every Fermion mass in nature exists because the Higgs field builds that bridge, which is exactly why the top quark's grip on the Higgs is so brutal. Now imagine a quark whose halves are identical twins. Both halves feel the weak force the same way. Both look the same to every law in the book. Physicists call this a vector-like quark, and it has a spectacular property. Its two halves can bond directly to each other, with no bridge required. That quark has a mass all by itself, written into the equations from the beginning, owing the Higgs field nothing, which means it can be arbitrarily heavy without any consequence at all. A vector-like quark weighing 1,000 times the top quark causes no problems whatsoever, because its mass never came from the Higgs in the first place. Every ordinary quark that heavy would tear the theory apart. Here is why anyone cares. If such a quark exists and mixes slightly with the top quark, the two of them share the burden. The vector-like quark contributes to the Higgs mass, with a term that partially cancels the top quark's shove. The runaway softens, the tuning eases. This is the engine inside almost every composite Higgs model, and it appears in extra dimension theories as well. Different mathematics, same rescue. Physicists call these top partners, and they are one of the most heavily hunted objects at CERN. They would be findable too. A vector-like top partner carries colour charge, so the Large Hadron Collider makes them in pairs whenever it has the energy. Each one decays in one of three ways: into a top quark and a Higgs, into a top quark and a Z boson, into a bottom quark and a W boson. Those are loud signatures. Multiple bosons, multiple heavy quarks, enormous energy dumped into the detector. A single clean event would be unmistakable. Atlas and CMS have looked for all three in every combination through the entire Run-2 dataset. The limits now sit above roughly 1,400 billion electron volts, and in some channels higher. Notice the pattern by now. The stop, gone below 1300. The gluino gone below 2200. The composite constituents pushed above 1000. The top partner pushed above 1400. Every visible rescuer has been chased out of the room the collider can reach. Every single one of them shares a property, and it is the property that made them findable. They all carry colour charge. They all feel the strong force. That is why the machine could manufacture them in bulk, and that is why their absence hurts so much. In 2005, two theorists asked a question that sounds like cheating. What if the top quark's partner feels no strong force at all? What if it carries no electric charge, no colour, nothing our detectors are built to grab? What if it lives in a mirror world that shares only gravity and the Higgs with our own, and the reason we have found nothing is that there was never anything to find? In 2005, three physicists asked a question that felt like a cheat code. The problem, stated plainly, was that every rescuer physics had imagined carried colour charge. Colour is the property that makes a particle feel the strong force, and it is the reason the Large Hadron Collider could hunt them. Protons are bags of colour-charged debris, so smashing protons together manufactures anything with colour in enormous quantities for free. That gift is also the trap. Anything the machine can easily make, the machine can easily rule out. And the machine had ruled them all out, so Zachariah Chacko, Hock Seng-go, and Ronnie Harnick asked whether the top quark's partner needed colour at all. Look back at why the cancellation works. The top quark shoves the Higgs mass upward, because it grips the Higgs field with maximum strength. The stop shoves back because it grips the Higgs with equal strength and belongs to the opposite family. Colour plays no part in the rescue. Colour is a side effect of the top quark being a quark. Strip it away and the cancellation still works perfectly. The theory they built is called the twin Higgs, and it says there is another copy of the universe layered on top of our own. A mirror sector. Its own photon, its own gluons, its own electrons and quarks, its own forces with their own strengths. Every particle there is invisible here because it feels none of our forces. Mirror light passes through your body without a flicker. Mirror matter falls through the Earth. The two worlds share exactly two things. They share gravity, and they share the Higgs. A mirror-top quark exists in that sector, gripping the shared Higgs field with the same crushing strength ours does. It contributes to the Higgs mass with the opposite sign. The mountain cancels, the tuning disappears. The Higgs sits at 125 for a good reason, and the rescuer is invisible. The Large Hadron Collider could run for 1,000 years and never make one directly, because the machine collides protons. Protons carry our colour charge, and the mirror-top quark ignores it entirely. A mirror world could be sitting inside this room, inside your chest, overlapping every atom you're made of, weighing something, gravitating, and touching nothing. Physicists call the idea neutral naturalness, and it landed like a slap. Every search program at CERN had assumed the rescuer would be loud. This says the rescuer was always quiet, and the 20-year hunt was aimed at empty air. That would explain everything. The silence from the stop searches, the silence from the Gluino searches, the silence from the top partner searches. Nature solved the problem in a way our detectors are structurally incapable of seeing, an idea that explains all evidence by predicting nothing is worthless, and the theorists knew it. So they went looking for a crack. They found one, and it comes from the single bridge between the worlds. The Higgs touches both sectors. That is the whole point of the construction. So a Higgs boson made in our collider can decay into mirror particles, and those mirror particles fly out of the detector untouched. The event would show a Higgs being born and then simply ceasing to exist. There is a way to catch that. It requires counting the Higgs bosons that vanish, and comparing the number against the ones that stay. You can weigh a ghost by watching what it fails to carry away. The trick at CERN is momentum. When two protons collide, the total momentum sideways to the beam is zero, because they hit head-on. Add up everything the detector sees flying outward, and the vectors must balance to zero. Every time. Conservation of momentum is as close to sacred as physics gets. So when the sum comes out wrong, something invisible left. Now use that on the Higgs. Physicists select collisions where a Higgs boson is produced alongside a loud, unmistakable companion. Two jets flying far forward at shallow angles, for instance, a signature that only appears when two W bosons fuse together to make something. The companion tags the event. It says, a Higgs was born here. Then they look at where the Higgs should be. If it decayed the ordinary way, into bottom quarks or photons or W bosons, the debris shows up and balances the books. If it decayed into mirror particles, the detector sees the tag, and then nothing. A hole in the momentum shaped exactly like a Higgs. The standard model already allows a tiny version of this. A Higgs can decay into two Z bosons which each become neutrinos, and neutrinos escape. That happens about 1 time in 1,000, which is far too rare to matter. So any excess belongs to something new. Atlas and CMS have run this measurement across every dataset they have. The answer keeps landing at 0, and the limit keeps tightening. Today, they can say that fewer than roughly 1 in 10 Higgs bosons vanishes into invisible products. That number sounds weak. It is the most powerful statement in the entire mirror world story, because it is the only statement possible. Think about what is being constrained. An entire hidden copy of physics, a full sector of particles with their own forces, is being squeezed by one measurement of things that fail to appear inside a machine in Switzerland. The high luminosity upgrade will push that limit down toward a few percent. At that point, large families of twin models begin to die. There is a second crack, and it is stranger than the first. In many mirror sectors, the twin particles bind into lumps, exactly the way our quarks bind into protons. Those lumps, called twin glue balls, live a long time. Some of them can decay back into our world, into ordinary particles, because the Higgs bridge works in both directions. The lump gets made at the collision point, flies outward invisibly for a few inches, and then, in the middle of the tracking layers, explodes into a spray of ordinary matter. A shower of particles blooming out of nothing, pointing nowhere. Physicists have started hunting exactly that. The searches are new. The techniques are awkward, and the trigger electronics were never designed for it. So far, nothing has bloomed. Every idea in this story shares one assumption, and it has gone unquestioned for 50 years. That the Higgs mass was set once, at the beginning, and has held that value ever since. In 2015, 3 physicists suggested the number was chosen later, by a field that went hunting for it. Every solution so far uses the same strategy. Find a symmetry, add a partner, cancel the shove. In 2015, Peter Graham, David Kaplan and Sujit Rajendran published a paper that abandoned the strategy completely. Their idea starts with a question nobody had thought to ask. What if the Higgs mass was never fixed? What if, in the first instance of the universe, it was a dial that turned, sweeping through every possible value from the Planck scale downward until something stopped it? They called the mechanism the relaxation. Here is how it works. Add one new field to the universe, extremely light, with a gentle slope built into its potential. Picture a ball on a hillside with a slight incline, rolling slowly, taking an eternity to travel any distance. Now connect that field to the Higgs. As the relaxation rolls, the Higgs mass changes with it. Early on, when the relaxation sits high on the hill, the Higgs mass is enormous near the Planck scale, exactly where the naive calculation says it belongs. The relaxation rolls, the Higgs mass drops, slowly, steadily, through 100 million billion possible values. Then it passes through zero, and the universe changes. Below that crossing point, the Higgs field switches on. Quarks acquire mass for the first time, and the moment quarks have mass, a new effect appears, generated by the strong force, which carves ripples into the relaxation smooth hillside. The gentle incline becomes a staircase. The ball, still rolling, hits the first step and stops. It stops at the exact moment the Higgs mass became small, not by luck, by construction. The barrier that halts the roll exists only because the Higgs turned on, so the field can only freeze where the Higgs is tiny. The universe scanned every possible value and then locked itself into the one that lets atoms exist, and it did so automatically, with no fine-tuning and no partner particles anywhere. That is a genuinely different way to solve a problem in physics. Every previous fix explained why the number stays small. This one explains why the number arrived at small. The idea has a cost, and the cost is a demanding early universe. The rolling must happen during an enormously long stretch of inflation, far longer than most models assume. The relaxation must travel an absurd distance in field space. Theorists have argued about whether the construction is even consistent since the day it was published. It also leaves a fingerprint, which is the only reason it counts as science. The relaxation has to survive to the present day, sitting in that staircase, mixing very slightly with the Higgs. That mixing makes it a light particle that couples to matter with feeble strength, which means it could be hunted by experiments that fire intense beams into thick walls and look for anything that passes through, by atomic clocks watching for a field that makes the constants of nature shift by a whisper, by tabletop instruments looking for a fifth force operating over inches. Nothing has been found. Every solution in this story has treated the Planck scale as real, a hard wall 100 million billion times above us. In 1998, 3 physicists suggested the wall does not exist. Hold a paperclip above a magnet and watch a scrap of metal beat the entire Earth. The whole planet, 6,000 billion tons of it, pulls the paperclip down. A magnet the size of a coin pulls it up and wins instantly without effort. That is gravity's dirty secret. Compared to every other force, it is pathetic. Electromagnetism beats it by a factor with 36 zeros. The strong force beats it by more. Physicists have stared at that gap for a century and mostly filed it away as a fact of life. In 1998, Nima Arkani Hamed, Savas Dimopoulos and Gia Dvali noticed that gravity's weakness and the Higgs problem are the same number. The Planck scale is defined by gravity's strength. Gravity is feeble, so the Planck scale is enormous. So the Higgs correction is catastrophic. Fix gravity and the entire hierarchy problem evaporates in one stroke. So they asked what would happen if gravity was secretly as strong as everything else and only appeared weak because it was leaking. Picture the universe as a sheet of paper. Everything you know about leaves on the surface. Quarks, electrons, photons, all of it. Stuck to the sheet, sliding around in 3 dimensions, unable to leave. Gravity is different. Gravity is a property of space itself, so gravity has no obligation to stay on the paper. It spills off the edges into dimensions we cannot see. Now the weakness makes sense. Gravity starts out just as strong as the other forces, then it spreads into the extra room, dilutes, and by the time it reaches us only a trace is left. A sprinkler firing in every direction while we stand under one droplet. If that picture is right, the Planck scale we calculated is a mirage. It is what you get by assuming gravity has always been feeble, all the way down. The true scale, where gravity becomes strong, could sit within reach of our machines, and the Higgs problem simply disappears. The runaway calculation had nowhere to run. The proposal made a prediction that anyone could test with a table and a wire. Gravity's inverse square law should break down at short distances, once you probe distances comparable to the extra dimensions themselves. So experimenters built torsion balances of absurd delicacy, hunting for a deviation in how two masses attract over spans smaller than a grain of rice. They have measured gravity down to a fraction of a millimetre and found Newton, unbroken, exactly as written in 1687. A refined version arrived a year later from Lisa Randall and Raman Sundram. In their construction, the extra dimension is warped rather than large, and mass scales get stretched as you move across it. The Planck scale on one side becomes the Higgs scale on the other, purely from the geometry of the gap. The huge number comes out of an exponential for free. Both versions predicted something spectacular at the Large Hadron Collider. If the true gravity scale sits a few thousand times the proton mass, then colliding protons hard enough would squeeze so much energy into so small a volume that gravity would take over. The collision would collapse. CERN would manufacture black holes. In 2008, a man in Hawaii sued to stop the Large Hadron Collider from turning on. The lawsuit named the United States Department of Energy and CERN. The claim was that the machine would produce a black hole, that the black hole would sink to the center of the Earth, and that it would eat the planet from the inside out. Newspapers ran the story. Death threats arrived at CERN. A teenager in India took her own life after watching coverage of the doomsday reports. The physicists were furious, and underneath the fury sat an awkward truth. They actually were trying to make black holes. The prediction is straightforward inside the extra dimension theories. If gravity becomes strong at a few thousand times the proton mass, then two protons colliding above that threshold would come close enough, hard enough, to trap themselves inside their own gravity. Space would pinch shut. A microscopic black hole would form, and then it would die, immediately, in the most spectacular way physics allows. Stephen Hawking proved in 1974 that black holes radiate. Smaller holes radiate faster and burn hotter. A black hole the size of a proton would evaporate in a span too short to write down, spraying every particle in the standard model outward in a chaotic, democratic burst. Quarks, leptons, photons, all in roughly equal numbers, flying in all directions at once. That signature is unmistakable. Ordinary collisions produce narrow sprays along preferred directions. A dying black hole produces a starburst, dozens of energetic objects filling the detector. So Atlas and CMS looked. They counted events with enormous total energy and huge numbers of outgoing particles. They looked for the starburst. The results excluded microscopic black hole production up to thresholds around 9 or 10,000 times the proton mass depending on the model. The Earth was never in danger, and the physicists knew it from the start. A hole that's small evaporates before it can travel the width of an atom. It has no time to eat anything, and no appetite either, since its gravitational reach is smaller than a proton. The theory took the damage instead. Every extra dimension model that solved the hierarchy problem needed the gravity scale within reach. Push it above 10,000 and the solution stops solving anything. The gap between the Higgs and the true gravity scale reopens smaller than before, and the tuning creeps back in. Notice the shape this story keeps making. Supersymmetry, silence. Compositeness, silence. Top partners, silence. Extra dimensions, silence. Black holes, silence. Every idea that predicted something visible has been chased into a corner where it no longer explains the thing it was built to explain. Physicists now use a phrase for this, and they say it with a flat voice. The nightmare scenario. A Higgs boson, nothing else, and a machine that keeps confirming a theory nobody believes is complete. There is one instrument left that has barely been used. It does not require making the new particle at all. Heavy things leave marks on light things, even when they never appear. In 1846, a French astronomer found a planet by staring at a different planet. Urbain Le Verrier watched Uranus drift off schedule. Its orbit disagreed with Newton by a tiny amount year after year. Rather than blame the theory, he assumed an unseen mass was tugging, and he calculated where it must be. He mailed the coordinates to Berlin. An astronomer pointed a telescope at the spot that same night and found Neptune within an hour. Nobody saw Neptune first. They saw its fingerprint on something else. Particle physics has the same tool, and it is now the sharpest one CERN owns. Any new heavy particle, however heavy, contributes to the boiling vacuum. It appears virtually, briefly, inside processes that we can measure. It never has to be manufactured. It never has to be seen. Its existence bends the numbers anyway. So point that at the Higgs. The Higgs grips every massive particle, and the strength of each grip is predicted exactly by the standard model. Measure the grips. If a new particle exists anywhere, mixing with the Higgs, or feeding into its production, the grips drift away from prediction. The drift shrinks as the new particle gets heavier, and it shrinks fast with the square of the mass. A particle 10 times heavier leaves a mark 100 times fainter. That is the brutal arithmetic of the method, and it is why precision matters more than energy here. Atlas and CMS have measured the Higgs gripping the top quark, the bottom quark, the tau, the W and Z bosons. They have measured it gripping the muon, which required finding a decay that happens roughly 2 times in 10,000, buried under a mountain of ordinary background. Every grip so far matches the standard model, within uncertainties of roughly 5 to 10%. Sit with what that means. A theory written in the 1960s, on a chalkboard, by people who had no idea what the Higgs weighed, predicts every one of these numbers correctly. 10 separate measurements, 10 hits. The precision is the whole game. At 10%, new particles can hide above roughly 1,000 times the proton mass. At 2%, that reach roughly doubles. Every factor of improvement in measurement buys a factor in mass reach that no energy upgrade could deliver cheaply, which means the search has quietly changed character. For 30 years, hunting new physics meant building a bigger hammer and looking for a new object in the wreckage. Now it means measuring the object we already have with obsessive care and waiting for a number to slip. There is one coupling in that list that has never been measured properly. It is the most important one, and it is the hardest thing the Large Hadron Collider will ever attempt. Every measurement so far describes the Higgs touching something else. None of them describe the Higgs touching itself, and the way the Higgs touches itself is the shape of the bowl. Everything in this story rests on a shape nobody has ever seen. Go back to the bowl. The Higgs field sits at the bottom of a curved potential, and the curvature at that resting point gives the Higgs boson its mass. We measured that. 125. That measurement tells you about one point. It tells you the steepness at the very bottom, where the field rests and nothing else. Move away from the resting point, out along the walls, and the shape becomes an assumption. Physicists assumed a specific form because it's the simplest thing that works. In that form, the entire potential is fixed by 2 numbers, both of which we know. Draw the bowl, and it draws itself. That assumption is the least tested claim in the standard model. Here is how you test it. The curve away from the resting point controls how strongly the Higgs field pushes on its own presence. Physicists call it the self-coupling, and it has one observable consequence. Once in a great while, a single collision produces 2 Higgs bosons at the same time, born together from one event. Only a pair carries information about the field touching itself. A single Higgs never involves it. There is no shortcut, no clever indirect route, no way to back it out of easier data. So CERN chases pairs. The problem is the rate. Making one Higgs boson is already rare, roughly 1 collision in a billion. Making 2 together is rarer by another factor of 1,000. Across all of Run 2, out of an amount of data that took years to collect, the machine produced a few thousand Higgs pairs in total, scattered across every possible decay pattern, buried under backgrounds that outnumber them by enormous factors. Neither experiment has found them yet. What they have is a limit. that limit already does work. The measured constraint says the self-coupling sits somewhere in a range around the predicted value, ruling out the wilder possibilities. The bowl has walls. The walls are roughly where they should be. Roughly is doing violent labour in that sentence, because the shape of the bowl decides more than the Higgs mass. It decides what happened to the universe when the Higgs field first switched on, a trillionth of a second after the beginning. A different curve means a different transition, possibly a violent one, with bubbles and collisions and gravitational waves still ringing today. It may also decide whether matter exists at all. The universe contains vastly more matter than antimatter, and nobody knows why. Certain shapes of that potential would produce the imbalance naturally during the early transition. The standard model shape produces nothing, so the same measurement touches the hierarchy problem, the birth of matter, and the earliest instant we can reason about. And it touches one more thing, which is the darkest possibility in physics. The bowl determines whether the ground the Higgs field rests on is truly the bottom, because when physicists take the measured numbers and follow the walls outward, past everything we can test, to energies far above anything we will ever build, the curve does something that nobody wants to talk about at parties. It turns over. Values in physics change depending on how hard you look. That sounds like nonsense, and it is one of the deepest truths in the subject. Measure the strength of electricity at everyday distances, and you get one number. Measure it by smashing particles together at high energy, probing much smaller distances, and the number grows. The virtual haze around a charge screens it, so the closer you get, the more of the true charge you see. Every quantity in the standard model behaves this way. Physicists call the drift running, and they can calculate it precisely. Now run the Higgs potential. The steepness of the bowl's walls has a value at everyday energies, fixed by the Higgs mass we measured. Ask what that steepness becomes at higher energies, and the equations answer with a tug of war. The Higgs pulls one way. Its own self-interaction pushes the walls upward, keeping the bowl steep, keeping the floor solid. The top quark pulls the other way. With that maximum grip, virtual top quarks reach into the calculation and drag the walls down, flattening them, and then bending them below the horizontal. The same particle. Again. The top quark destabilizes the Higgs mass, and then, in a completely separate calculation, it destabilizes the floor the Higgs field rests on. Run the numbers with the measured masses, and the walls flatten out somewhere around 1 billion times the mass of a proton. Push higher and they turn downward and keep falling, which means the bowl is a hillside. Our resting place, the vacuum we live in, the ground state of the universe, sits in a shallow hollow near the top of a slope. Somewhere far out in field space past a hill we cannot see over, the potential drops into a valley deeper than the one we occupy. The vacuum is a ledge. Understand the stakes. If the Higgs field ever found its way over that hill, it would roll into the deeper valley, and everything anchored to the field would change. Particle masses would take new values. Atoms would stop being possible. Chemistry would end. The universe would become a different universe, running different rules, containing nothing that could ever wonder about it. Now hear the part that should be said immediately and loudly. There is no danger. None. The barrier between our hollow and the drop is so enormous, and the probability of crossing it so grotesquely small, that the expected waiting time exceeds the age of the universe by a factor with hundreds of zeros. The sun will die, the galaxies will drift apart, the last star will burn out, the protons themselves may decay, and the vacuum will still be sitting exactly where it is. Nobody is losing sleep. That should be clear. The reason physicists care has nothing to do with fear and everything to do with what the arrangement implies. Because when you plug in the numbers and ask which side of the boundary we land on, stable or metastable, the answer comes back at the edge, right at the line, balanced within the uncertainties between two completely different fates. The universe appears to be tuned to sit exactly on the knife, and nobody has any idea why. Draw a map with two axes. Along the bottom, the mass of the top quark. Up the side, the mass of the Higgs boson. Every possible universe with these two ingredients has a spot on this map. Now paint the regions. One region is stable. Universes there have a Higgs potential that keeps rising forever. A flaw that is truly a flaw. a vacuum that lasts as long as anything can last. Another region is unstable. Universes there collapse almost immediately, within fractions of a second of their birth, because the barrier is thin and the drop is close. Between them sits a strip, metastable. The floor is a ledge, and the barrier is so enormous that nothing will ever cross it in any span that has meaning. Physicists have drawn this map many times, and it hangs in offices around the world. It is one of the most quietly disturbing images in modern science. Our universe lands in the metastable strip close to the boundary with stable. The boundary line runs across the map. Our dot sits within a couple of steps of it. Shift the top quark mass down by roughly 1 part in 100 and the dot crosses into the stable region. Shift it up by a similar amount and metastability deepens. We are balanced within a percent of the line, separating two completely different destinies for existence. Understand how strange that is. The Higgs mass was set by whatever wrote the laws. The top quark mass came from the same place, through a different mechanism, with no known connection between them. Two independent numbers, arriving from unrelated corners of physics, land the universe within a hair of a boundary that neither of them knows about. Nobody predicted this. Before 2012, the Higgs could have been anything. When the number came in at 125, the theorists ran the calculation and found the dot landing on the edge, and a quiet unease entered the field that has never left. There are 3 ways to read it. The first reading is coincidence. 2 numbers landed near a line. Lines exist, numbers land near them, move on. The second reading is a clue. Something in the deep structure of physics wants the universe to sit here, and the near miss is a message written in the only language nature uses, which is arithmetic. Some theorists have built entire frameworks on the assumption that criticality is a principle, rather than an accident. The third reading is the most unsettling. Perhaps the universe sits here because a stable vacuum requires new physics we would have noticed, and an unstable one kills you instantly, and the metastable strip is simply the only place observers can exist to draw the map. Every one of those readings depends on the dot being where we think it is, which brings the entire story to a single number, measured by a handful of collaborations, quoted to 3 decimal places in every review paper written since 1995, the mass of the top quark. And there is a problem with that number that most physicists outside the field have never heard about. The value we measure with such spectacular precision may not be the value the equations are asking for. The top quark mass is known to about 2 parts in 1,000. It is one of the most precisely measured quantities in particle physics, extracted from millions of collisions, cross-checked across 2 experiments and 2 continents, refined for 30 years, and a genuine argument exists over what it means. Start with a fact that sounds like a technicality, and turns out to be the whole problem. The top quark never exists on its own long enough to be weighed. It decays before the strong force can even grab it, in less time than light takes to cross a proton. There is no moment when a top quark sits still, isolated, waiting for a scale. So how do you weigh something that has never been at rest? You reconstruct it. You collect the debris, the bottom quark jets and the leptons and the missing momentum, and you feed the numbers into an enormous simulation of what the collision should have looked like. Then you turn a dial inside that simulation, labelled top quark mass, until the simulated events match the real ones. The number you extract is the value that makes the simulation agree with reality. That number is called the Monte Carlo mass, and it belongs to the software. The equations that decide whether our vacuum survives want a different quantity. They want a mass defined inside quantum field theory, cleanly, with a precise mathematical meaning. Physicists call it the pole mass, and it is what appears in the running calculation that bends the Higgs potential. The two are close. Nobody knows exactly how close. Translating one into the other requires understanding how the strong force dresses the top quark in the moment before it dies, and that dressing involves the messiest part of physics. The best estimates put the ambiguity somewhere around a few tenths of a percent, comparable to the entire experimental uncertainty. Now look back at the knife edge map and feel the floor tilt. The distance from our dot to the stability boundary is roughly 1% in the top quark mass. The ambiguity in what the top quark mass even means is a sizable fraction of that distance. The most disturbing structural fact about the universe rests on a number whose definition is under active dispute. Physicists have attacked this from every angle. They measure the top quark mass from the production rate instead of the decay debris, which gives a theoretically clean quantity at the cost of much larger uncertainties. They measure it from the shape of energy distributions. They compare methods and watch them disagree by amounts that make everyone uncomfortable. The disagreements are small, they sit exactly where they hurt most. So the fate of the vacuum, the stability of the ground beneath all of existence, currently hangs on a definitional argument about a particle that lives for a span too short to imagine. Nothing in physics illustrates the gap between precision and understanding more brutally. Suppose the pessimistic reading is right. Suppose our vacuum truly is a ledge, and the drop is real, and somewhere in the eternity ahead the Higgs field finds its way across. What does that actually look like? The answer was worked out in 1980, and it is the most terrifying calculation ever published in a physics journal. Sidney Coleman spent the 1970s working out how a universe ends. He did the mathematics with Frank DeLucia, published it in 1980, and the resulting paper is one of the strangest documents in the literature. It is a careful, technical, entirely serious calculation of the destruction of everything, written by two people who found the problem interesting. Here is what they found. The Higgs field does not roll over the hill, it goes through it. Quantum mechanics allows a system to appear on the far side of a barrier it lacks the energy to climb. Radioactive decay works this way. So somewhere, someday, in some tiny volume of space, the Higgs field will tunnel. A region the size of an atom will flicker into the deeper valley while everything around it stays put. Most of these attempts fail instantly and heal over. The new region costs energy at its surface, and the surface tension crushes it out of existence before it can grow. Then one attempt is born slightly too large. Past a critical size, the energy gained inside beats the cost at the boundary, and the region grows, and once it starts growing, nothing in physics can stop it. The wall accelerates outward, converting energy into motion, until it moves at effectively the speed of light. A bubble of true vacuum, expanding at light speed, forever. Inside the wall, physics is different. Particle masses take new values. The rules that hold atoms together are gone. Everything the bubble touches stops being what it was, instantly, with no transition, and no wreckage worth describing. And here is the part that makes the calculation genuinely unpleasant. The wall travels at light speed, so does every possible warning. There is no signal that can outrun it, no telescope that could see it approaching, no early flicker in the sky. The bubble arrives at the same moment as the news of the bubble. You would experience nothing at all. Not a flash, not a sound, not a fraction of a second of awareness. The universe would end for you before any nerve could fire. Coleman and DeLucia noted with dry humour that after such an event the situation would offer no consolation to anyone, since life as we understand it would become impossible, and also that any physicists inside would have no time to appreciate the confirmation of their theory. Now the numbers, because the numbers are the point. The expected waiting time for a bubble to nucleate anywhere in the observable universe is unimaginably long. Estimates run past 100 zeros, and in many calculations far past that. The universe has existed for 14 billion years, which is a rounding error against a number like that. Every star will die, every galaxy will scatter, every black hole will evaporate, and the vacuum will still be sitting undisturbed. There is no reason for concern, and physicists say so every single time this comes up. Still, one question refuses to die, and the public asks it every time CERN turns the machine on. If our vacuum is a ledge, and colliders concentrate more energy into a smaller space than anything else on Earth, could we push it? The answer is no, and the proof is beautiful. Nature has already run the experiment trillions of times at energies that make CERN look like a toy. On the night of October 15th, 1991, a detector in the Utah desert recorded a single particle carrying the energy of a fast baseball. They named it the Oh My God particle, one proton, one subatomic speck, arriving from somewhere in the sky with about 40 million times the energy the Large Hadron Collider can give anything. It hit the atmosphere and produced a shower of debris that spread across miles of desert air. Nobody knows what accelerated it. Particles like that arrive constantly. The atmosphere above your head is being hit by cosmic rays right now, every second, some of them carrying energies that dwarf anything we can produce. They have been arriving for as long as the Earth has existed. In 1983, Piet Hoot and Martin Rees turned that fact into a proof. Their argument is simple enough to follow in one breath. If a high-energy collision could trigger vacuum decay, the universe would already be gone. Cosmic rays have been smashing into things at energies far beyond our machines for billions of years, everywhere, in every galaxy. The number of such collisions in the history of the universe exceeds the number the Large Hadron Collider will produce in its lifetime by a factor with dozens of zeros. The sky is still here, therefore those collisions are safe. Therefore ours are too, by an enormous margin. The argument has a hole, and CERN's safety group closed it. Cosmic ray collisions happen in flight, so any dangerous object produced would fly away at nearly light speed and leave the planet. Collider collisions happen head-on, so a slow object could stay put. So they extended the argument to objects that stay put. White dwarfs and neutron stars are dense enough to capture anything produced inside them by cosmic ray collisions. Those stars have been bombarded for billions of years. They are still there. We observe them, in enormous numbers, sitting exactly where they should be, obeying exactly the physics they should obey. The universe has run every experiment CERN can run, at higher energies, for longer, in more places, and left the results in the sky for us to read. The vacuum has survived all of it. There is a deeper reason the fear was misplaced from the start. Triggering a transition requires pushing the Higgs field over a barrier that sits at energies around 1 billion times a proton mass, across a region of space large enough to keep growing. A collider concentrates a modest amount of energy into a volume smaller than a proton. The gap between what we can do and what would be required is not a difference of degree. It is a difference of 100 million billion, so the vacuum is safe, and the knife edge is a clue rather than a threat, and the search continues for what it always was. An attempt to understand why the numbers are what they are. For a while, in the last decade, it looked like the answer might arrive from an entirely different direction. 3 separate measurements began drifting away from prediction. Physicists started using the word crack, then each one was checked. For 15 years, the best hope in particle physics was a wobbling muon. The muon is a heavy cousin of the electron and it spins. Put it in a magnetic field and it wobbles like a gyroscope, at a rate the theory predicts to 12 digits. That rate depends on the boiling vacuum around it. Every particle that exists, including any we have never discovered, contributes to the wobble. So the muon is a scale that weighs the entire particle content of the universe, including the parts we have never seen. In 2001, an experiment at Brookhaven found the wobble drifting from prediction. In 2021, a new experiment at Fermilab, using a magnet that had been floated on a barge down the Atlantic coast and up the Mississippi, confirmed the drift. The gap grew more significant with every release. Papers poured out. Theorists proposed hundreds of new particles to explain it. The experiment finished its work and published its final measurement in 2025, with a precision better than anyone had promised. The problem turned out to sit on the theory side. Calculating the prediction requires knowing how the strong force contributes to the wobble, and that piece cannot be computed by ordinary means. For years, physicists derived it from other experimental data. Then supercomputer simulations of the strong force reached the required accuracy and delivered a different answer, and a new measurement in Russia disagreed with the older data as well. When the theory community produced its consensus prediction in 2025, using the improved methods, the prediction moved toward the measurement. The anomaly dissolved into an argument about the strong force. The same thing happened to the W boson. In 2022, a team in Illinois announced a measurement of its mass that sat far from prediction. After a decade of careful analysis, it made headlines everywhere. Then Atlas remeasured it. Then CMS remeasured it, with the most precise result ever obtained. Both landed on the standard model. The pattern here deserves respect rather than disappointment. Physics worked, a claim appeared, the community attacked it from every side, and the truth survived the attack. That process is the entire reason the subject is trustworthy. It also leaves the field in a bleak position. There is no anomaly to chase, no crack, no thread hanging loose from the fabric. The standard model has passed every test thrown at it for 50 years, including the ones designed specifically to break it, and it continues to describe a universe that its own equations say should be impossible. Physicists are left holding a theory that works perfectly and explains nothing about why it works, which forces a question that most of them have spent their careers refusing to ask. What if there is no mechanism? What if the Higgs mass is small for the same reason the Earth sits 93 million miles from the Sun? No principle, no symmetry, no hidden particle waiting to be found. Just selection, running across a landscape of universes, most of which contain nobody at all. In 1987, Steven Weinberg made a prediction that everyone hated, and nobody could refute. The subject was the cosmological constant, the energy of empty space. Theory said it should be enormous. Observation said it was essentially zero. The mismatch was worse than the Higgs problem by a wide margin, the largest disagreement between prediction and measurement in the history of science. Weinberg tried a different approach. He asked what values were compatible with anyone existing to measure them. Make the constant large and positive, and space expands so violently that matter never clumps. No galaxies, no stars, no observers. Make it large and negative, and the universe collapses before life could arise. Only a narrow window permits structure. So Weinberg predicted the constant would land in that window, near the largest value compatible with galaxies forming, and no smaller. 11 years later, two teams measuring distant supernovae found the expansion accelerating, and the constant landed roughly where he said. That prediction is the strongest argument for the idea most physicists find intolerable. The argument goes like this. There is an enormous landscape of possible universes, each with different constants, and they all exist. String theory suggests a number of possible configurations with hundreds of zeros in it. Inflation provides a mechanism for producing them, endlessly, in regions forever beyond our reach. In that picture, asking why the Higgs mass is small is like asking why your house has an address. It has one because addresses exist and you live somewhere, and there is a reason our address might be special. In 1998, 4 physicists ran the numbers on the Higgs. They asked what happens to a universe where the Higgs field strength is larger than ours. The answer is quick and brutal. Push it up by a factor of a few and quark masses change. The delicate balance that lets protons and neutrons bind falls apart, and complex nuclei stop existing. No carbon, no oxygen. A universe of hydrogen and nothing else, forever. So the window that permits chemistry is narrow, and we live inside it, and the anthropic reading says that is the entire explanation. Physicists loathe this for a reason that deserves respect. It predicts almost nothing. It cannot be tested. It ends inquiry rather than advancing it. Generations were trained to find mechanisms, and this replaces mechanism with real estate. The counter-argument has teeth too. Weinberg used exactly this reasoning and got the right answer while the mechanism hunters got nothing. A related possibility sits alongside it, and it is more sober. In 2004, Arkani Hamed and Dimopoulos proposed keeping supersymmetry while abandoning naturalness. Let the twin particles be enormously heavy. Accept the tuning as a fact about our address. Keep the parts that work, the dark matter candidate and the unification of forces, and discard the promise that anything would show up at CERN. They called it split supersymmetry, and it was an act of surrender dressed as a theory. So the field stands at a fork. Down one path, the mechanism exists and hides just past our reach. Down the other, there is no mechanism at all. Only one thing can settle it, and it is already being built. In 2026, the Large Hadron Collider is running the last stretch of its ordinary life. Then it stops, for years, and technicians go underground to rebuild it. The high luminosity upgrade replaces the machinery closest to the collision points, with magnets built from a superconductor that has never been used at this scale. Niobium tin, brittle as chalk, capable of squeezing the beams into a spot narrower than anything the current magnets can manage. Tighter beams mean more collisions per crossing. The goal is a factor of 20. By the time the project finishes in the early 2040s, the machine will have delivered roughly 20 times the data it has collected in its entire history so far. The cost is chaos. Each beam crossing will produce around 200 separate proton collisions layered on top of each other, in the same place, at the same instant. Sorting the interesting one out of that pileup requires detectors that can time each track to a few trillionths of a second, so the software can slice the collisions apart by when they happened. Both experiments are being rebuilt around that requirement. New trackers with more channels than any instrument ever made. New timing layers. triggers that rid out vastly more events than the current system permits, because the last 20 years taught everyone that the trigger throws away exactly what it was not designed to imagine. Here is what that machine will actually settle. Higgs couplings move from 10% to a few percent. That doubles the reach of the fingerprint method, pushing composite structure and mixed-in heavy particles well beyond 1,000 times the proton mass. Invisible Higgs decays drop from 1 in 10 toward a few in 100, which begins killing large families of mirror-world models. Higgs pairs become reachable. The projection suggests that combining both experiments should deliver the first real evidence of the Higgs touching itself, and a measurement of the self coupling to roughly half its value. The shape of the bowl finally gets tested rather than assumed. Stop searches extend a few 100 billion electron volts higher. Long-lived particle searches, now taken seriously, get purpose-built triggers for the first time, and here is what it will fail to settle. A stop hiding in the stealth window may stay hidden. A mirror sector with the wrong parameters escapes. A composite Higgs with constituents at several thousand times, the proton mass leaves fingerprints too faint to read at a few percent. The upgrade is a factor of 20 in data. The gap between the Higgs mass and the Planck scale is a factor with 16 zeros. By the early 2040s, physicists will know the Higgs boson better than any particle in history, and they may still have no idea why it weighs what it weighs. Everyone in the field understands this, which is why, while the upgrade proceeds, an argument has been running about what comes after and how much of it Europe is willing to pay for. That argument reached a conclusion 2 months ago, in Budapest, and it commits our species to a machine that most of the people who voted for it will never live to see finished. On the 22nd of May 2026, in a conference room in Budapest, the CERN Council chose a future. After more than 2 years of work by the European particle physics community and more than 260 written submissions from 36 countries, the Council updated the European strategy for particle physics and named the electron-positron Future Circular Collider as the preferred flagship project for CERN. The machine is a ring 91 kilometers around, roughly 57 miles, buried under the French and Swiss countryside and running in a wide arc beneath Lake Geneva. The current collider would fit inside it 3 times over. A feasibility study completed in March of 2025 concluded the tunnel could hold an electron-positron collider first, and then, decades later, a proton collider at the energy frontier in the same excavation. The first stage collides electrons rather than protons, which sounds like a step backward and is the opposite. Protons are bags of junk. When two collide, the interesting event happens between unknown constituents carrying unknown fractions of the energy, buried under debris. Electrons have no parts. Every collision is clean, known, complete. You can measure the Higgs boson to a fraction of a percent instead of 10. That precision is the whole strategy. The fingerprint method reaches new particles far beyond the energy of the machine itself, because the boiling vacuum tells on them. A ring like this would produce millions of Higgs bosons in clean conditions and measure every grip to a fraction of a percent, extending the reach for new physics by a large factor without ever making the particle. Then comes the arithmetic that makes this a decision about people rather than physics. The Council invited CERN's management to build a funding plan and set a target date of 2028 for the actual decision to proceed, taking into account financial feasibility and public consultation in France and Switzerland. Construction would run through the 2030s and 40s. First collisions in the middle of the century. The proton stage, the one that could reach the energies where the answer might live, arrives in the 2070s. A graduate student starting today would retire before the second stage turned on. So the field has committed to a search that outlives everyone conducting it, aimed at a question that has resisted every attack for 50 years, with a real chance that the answer is that there is no answer. Sit with the whole arc. Empty space boils. The top quark, the heaviest thing we know, shoves the Higgs mass toward a value 100 million billion times larger than what we measure. Something holds it down. Every candidate for that something has been chased into silence. The same top quark bends the floor beneath the vacuum, leaving our universe balanced on a knife edge nobody can explain, resting on a number whose definition is under dispute. And you are made of atoms that exist because the 35th digit came out right. Whatever holds the Higgs mass in place has been doing it for 14 billion years. in every cubic inch of space, including the space inside your chest. We have built the largest machine in history to find it, and it has told us nothing. So we are digging a bigger tunnel